So yes, as I say, welcome to data visualization with R and ggplot. And let me say a little bit about how we're going to get started today and be organized. Um, okay, so we've got our slides here, and let's get started with a little bit of housekeeping to just kind of give you an overview of what we'll be doing today and over the next couple of sessions. So as you know, if you're here live, we've got our current session, which goes about 2.5 hours. We'll take a couple of short breaks as we go, so we're not going to plow through kind of 2.5 solid hours, but then we'll take a full hour break at uh, at 12:30 Eastern time in the middle, and then back again for the afternoon session. Um, During the live session, if you're here, please feel free to ask questions in the chat. Is probably the most straightforward way to do things. You're welcome to raise a hand to speak as well, but generally typing a question or making a comment in the chat or asking for some clarification is a good way to do that, and then I can share that with the rest of the group. That's also good for people who will be following along asynchronously. And then in between class sessions, I really strongly encourage you to join the course Slack, the little discussion group that we have. That's a very good place to raise slightly more detailed questions that you might have or points of clarification. And obviously, if you're not watching live, then that's also your main channel of feedback. I will be monitoring what's going on in the Slack in between our sessions, and I'll do my best to answer questions that people might have there. That's also a good place. Sometimes people have questions that involve kind of bits of code of their own or specific sort of data questions, and that's a good place to raise those because we can share little code chunks and so on in the Slack. So please do take advantage of that if you have questions. Um, Let me say a little bit about how we'll be proceeding. And so we've got sort of like a few things that we'll be doing consistently throughout the course. I'll be talking here and as I go through the material. And then we have these slides that you can see here, and then we'll also periodically jump over to my Mac here on this other side, where we have a little coding environment that we can work in, and we'll be sort of going through bits of live code and stuff there as we go. I encourage you strongly to now, whatever works best for you, of course, but the course packet that was distributed beforehand is set up to make it somewhat easy for you to take notes about the course. We'll get to that in just a moment. And it's an RStudio project, which we'll talk more about as we go. And the whole thing is self-contained. It also contains all of the code or almost all of the code that we'll be using and writing during the course, and is just a good way to integrate the material that we'll be covering with any notes that you have any notes that you have yourself. Let me start just by getting that sort of in front of you, even if you don't have um, any prior experience with R, which we don't assume for the course. I know there's always variation with the people who sign up for this course. Some of you will have used R before a little bit. Others might be completely new to it. We'll start from scratch and we'll work our way up to what we need to know. And this course is kind of like both. The focus will be on data visualization, but writing R code to draw these graphs that we're going to want to draw is a very good way to kind of get into using the fundamentals of R and RStudio as well. And so we'll build that up. We'll build that up as we go, and we can launch. Let's just take a look here. Actually, we'll go over to the to our Mac Mini here, and then I can put myself up in the corner like this by magic. And if the course packet that you would have downloaded should include these files if you've unzipped them. And what we can do at the beginning here is to focus on this data_visualization.orproj, which is short for or project file. And if we double click on that like this, then it will launch RStudio, assuming that everything has been properly installed. And what you should find is sort of something that looks a little bit like this. At the very beginning, if you launch it, it may just look like this with this thing, the console on the left-hand side, with this command prompt here, and then over here, if you click on the Files tab, you'll see a list of the files that are in this folder, and you can start with this course notes.rmd file, which is sort of set up to be your notes document for the course. And don't worry at this point if RStudio is unfamiliar to you, if this looks sort of slightly overwhelming with respect to all of these different panes and all of these different tabs and so on. That's a lot of text. RStudio is this integrated development environment, or IDE, for writing our code. There's a lot that you can do in it, and we'll get introduced to it as we go in the first session today. You can try and make sure that everything is working to knit your document here just by clicking this knit button, and what should happen is that you get this kind of flash of activity. It switches over to this render panel here, and you get this slash of junk, and then either in your viewer or popped out into a browser, you should get this formatted text, which corresponds to what we have over here, and it's got a bunch of code that gets executed, and then we scroll down here to where we're starting with this admonition to look at your data, and there's like this little bit of code chunk that's here. Now, as I say in the slides, don't worry if it's not clear kind of what's happening at this point, or if you haven't used it already. We'll go through it in detail as we go, but we can try to write a little bit of code just kind of right away to see what we can do here, and knit our document again. And I encourage you to sort of actually write this in this little chunk here. We'll go back over to this. In this little bit here in line 74 to 75, you can see that the text is the shading is a little darker. This is like a special chunk where we can write code as opposed to chunk, and you can just follow along and write, for example, library tidyverse and library gapminder, like that. And then we will draw a plot. We will write the less than sign and the dash to give us this little arrow. And don't worry if yours doesn't look as nice an arrow as that. That will work. And we say data equals gapminder, comma, mapping equals AES, we'll open parentheses, X equals GDP per cap, with a capital P there. Gotta watch out for that. You'll see me as we go make lots of typos, which is a standard feature of programming. So don't worry too much if you don't get this right first time. But we can do that, and then type P plus jom under. Oh, see, I just made one right there on purpose. Jom underscore point, like that, and then if we save our document by going up here to this save icon. This icon, I'm just looking at our audience here. It's like nobody knows what this is anymore. This icon here. This is a 3.5-inch floppy disk, which hasn't existed but it means save to disk. So we click that, and now it saves. My daughter saw one of those recently in an assignment, and she was like, "Oh, you got to put it, you got to click the fancy folder button." She said to me, "Dad," and I said, "What do you mean the fancy folder button?" And she said, "This. It looks like a fancy folder." And it's like, that's not a fancy folder. That's a 3.5-inch disk. Um, so the persistence of these user conventions, and we will knit our document again by clicking up the knit button, and uh, and we have sort of very quickly, if we have successfully done this, uh, as it's processed, there we go, written our first code and made our first plot. As I say, not to worry if we don't know exactly what this incantation over here means, but that lets us verify that things are working. So this is the environment that we're going to be working in, and we will discuss in detail exactly how the IDE works, and then how the code itself produced this plot, and a whole bunch of other detailed information as we go. This is what we're going to get familiar with. But for this first session, for the next hour or so, we'll take a step back, and instead of writing our code directly and jumping right in, we'll talk a little bit about the principles of data visualization and why it is that we care about visualizing our data, and what principles we have in mind when we're trying to draw graphs that are good to look at, that are informative and helpful either to ourselves or to our audience as we explore and present our data. So we'll just take a step back and get a little bit on the bigger picture about how to think about this generally. And then we will introduce ourselves to the tools that R provides us with for implementing those principles as we go. So we start from the general idea that you should look at your data, that this is a useful thing that you can do, and an important thing that you should do as you go, and let's talk about sort of why that is. Why is it that sort of looking at things and seeing things in our data is a useful activity? Well, a conventional place to start in answering that question is Anscombe's quartet here, which is a deliberately constructed, a made-up little mini data set consisting of these 4 different sub-data sets. And the idea, as I said, this was just kind of made by Anscombe quite some time ago now. The idea is that we've got 4 sets of pairs of observations, and if we summarize them numerically, that is, each of these panels has 11 data points in it with some x and y relationship. If we calculate the means, if we calculate a little bivariate regression, if we draw the best fitting line between them, we will get the same answers numerically for each panel. And so you see some of that just kind of down here. That this is the slope. You'll get y is 3 on half of x. The standard error of the slope estimate is this for all of these panels. And so were you to kind of naively just look at the numerical summaries of the relationship between these different little mini data sets, you might think that they were the same. But by looking at them, we can immediately see that whatever is going on with the data generating process, it's different in each case, right? And by visualizing it, we see that point gets made kind of immediately for us. Now, this is a made-up bit of data, but that kind of that benefit of looking at data as a way of kind of exploring and confirming aspects of it is extremely useful, and this sort of thing pops up in real life, kind of surprisingly, and in the real sort of scientific literature, surprisingly often. This is a paper from the late 1970s, and this is actually a reply or a comment on a paper that was published in the American Sociological Review in around 1980. And the original paper had made this argument that there was a positive relationship between voter turnout and a negative relationship between voter turnout and income inequality in a bunch of OECD countries. This was back in the good old days of quantitative research, where you could get into ASR with a small regression with 18 observations, and so the idea is that sort of as voter turnout goes up, the income inequality in the country goes down. And the purpose of this comment, which consists almost literally of just this graph with a very small amount of explanatory remarks, is that the original data set includes South Africa with the data from the 1970s. At a time when, well, the reason that, but counted in its it counted the whole physical population of all the people living in South Africa, but of course, 90% of them weren't able to vote because of apartheid, and this, and then South Africa, by the same token, is a country with a great deal of income inequality, and so this outlier here has immense leverage over the original regression slope that gets estimated, and if you remove it, then the association between voter turnout and income inequality becomes spectacularly less significant or interesting, at least in this data set. Now, the thing here is that, like, it's not as if numerically it would be impossible to discover this fact, or even if you were just sort of aware of your own data, that you would, it's not that sort of the graph is magically the only way to find this out, right? And that will be a theme kind of throughout this course. Visualizing data is just one tool that we have amongst many necessary tools for investigating and presenting our data. And we'll actually spend a good chunk of time kind of thinking about the ways that data visualizations can go bad and can kind of fool us by mistake. So I don't want to give the impression right at the outset. I never think of data visualization as kind of this magical panacea that will sort of solve all the problems that you have. It's just one tool amongst many. But when it comes to presenting the data, at least this graph kind of makes the point directly and in a way that's kind of hard to gainsay. And you might think, well, this is the sort of thing that happens only 30 or 40 years ago, and we don't do this sort of thing anymore. But again, you'd be surprised how often we can get results presented that become immediately sort of clarified when we take a look at the data in a sort of visual manner. This, for example, is from a paper published in the ASR in 2016, investigating an important issue, which is the topic under investigation is kind of the relationship between community violence in this case in the city of Milwaukee in the United States, and willingness to call emergency services in the wake of a highly publicized incident of police violence against an African American man in Milwaukee. And what this graph is trying to show you is that in Milwaukee there was an incident of police brutality that was widely reported and is focused on sort of occurred in a poor, mostly African American neighborhood. And what this model is trying to estimate is what sort of effect the tendency, the propensity to call the police in the wake of some crime or emergency or anything else, emergency services generally, what happened in the wake of this widely publicized incident of police brutality. And the paper makes the argument that it had a significant negative effect on people's likelihood to have any trust in the police. Right. So it's an important topic. And the way that the model is specified is that we start from when the story broke, which was in March of the year, and then we look at the weeks before and after the story broke to sort of get the kind of comparison, right? So this is the sort of treatment of this event, and then we sort of see looking afterwards and looking before, was there a problem? Now, there was a comment followed up just a couple of years later by Michael Zurob, who argued convincingly that this that this model was kind of an artifact, that this finding was an artifact of the way that the model was specified, and the reason that, in his view, that this happened was that, well, just taking a look at the actual data here of when it comes to understanding when events happened, well, the the story broke in March of that year. Milwaukee's in the upper Midwest of the United States. It's very cold in the winter. Calls to the police follow a seasonal pattern, a strongly seasonal pattern, with more like when people are out in the summer or in the early fall, it's warmer and there's more things that happen. And in the winter, there's less public activity and there's less emergent calls to. As a result, there's fewer emergency calls to the police. There's one exception, which is the last week of every year, and that's New Year's Eve, when people do go out, and there are greater calls to the police, and it's this combination of the seasonality and these outliers that was driving this pattern, or this apparent pattern in the data, but we didn't see the original data in the original paper. But just by looking at the intense seasonality of the data and the fact that it was really it was the fact that this final week of 2004 was close enough to this precipitating event that allowed for an apparently statistically significant effect to be modeled. Now, you can do all kinds of more complicated modeling with this data, and you can go through a whole bunch of different specifications and so on. As I say, the visualization is just the beginning, but it's immediately clear, I think, like when this happens, how easy it is. Like, I don't think if the original authors had looked at the data in that way, that they wouldn't have chosen to specify their model like this, right? Because if you're just looking at numerical summaries, and if you're just looking at the data in particular, if you're just looking at slopes and lines and estimates without the underlying data, well, then you're just much more likely to make those kinds of errors. And the point is quite general, and I want to emphasize that it's something that happens both when we are presenting our results to other people and when we're examining data ourselves. A theme of this morning's session is going to be sort of that, we want to find patterns in our data, and often we will find them, right, if we look for them. People are very good pattern matching creatures, and so we have to be on the lookout all the time for kind of when it is that we're fooling ourselves. And so in this example, we have a whole bunch of different underlying data generating mechanisms, from the sort of classic never truly observe, normal X and normal residuals, everything is lovely, a bivariate, independent, identically distributed data, through to things like a curvilinear relationship, or some sort of a single positive outlier or single negative outlier, sampling at the extremes, coarse or categorical data, and so on, all of which will give sort of essentially the same bivariate kind of relationship numerically, but it's immediately obvious if you look at the data that it's not, we shouldn't just go ahead and fit this particular kind of model or whatever, and without looking first. And as I say, I think that point generalizes because across empirical investigation in the social sciences and public health and in medicine, we tend to undervalue the utility of just looking at descriptive scatter plots of the data, in part because there's often this pressure, either sort of externally or from ourselves as analysts. There's a tendency to kind of want to do the most complicated thing that you know how to do, and you sort of jump straight to that, like some sort, panel hierarchical time series, you just model it right away, jump to the really complicated stuff, as opposed to just kind of looking at the beginning at, like, well, what's plausible to say about this data? And visualization can help us a lot along these lines. And this point gets kind of made in a bunch of different ways, that just looking at your data can inform you of things about it in a way that wouldn't be obvious if you just simply looked at numerical summaries. This is the Datasaurus, who again is a sort of semi-serious generalization of Anscombe's quartet, which you can sort of arrange your data in all kinds of ways that has this structure that isn't immediately obvious from numerical summaries. So that's the first point. It's worth looking at your data. The second point, though, is that when you look at your data, you should always be thinking about, or when you present data, you should think about who is your audience and what did they know? Like how do they understand when they look at some sort of, a scatter plot, as in this case, or any other kind of way of visually summarizing your data. No less than you would think when presenting quantitative or model-based summaries of your data, you should think about sort of how easy it is for your audience to understand what it is that you're showing them. And so it's a mistake to think that just because something is being shown visually, that it's immediately obvious or that we can just grasp it directly. And instead, there's considerably more kind of interpretive work involved in even straightforward visualizations than you might think. This is data from or the results of a survey from Pew Research, who do a lot of good work presenting their data visually, but we're interested in what is the sort of base rate of comprehension of the sort of workhorse scatter plot here that we showing a relationship between something on the y-axis and something on the x-axis. And so they asked a representative sample of American adults, which of the following statements best describes the data in the graph. When I teach this in person in class and you ask for, people to suggest the answer, there's always this moment of kind of panic. Is that what, there's a trick with these kind of questions always. But we can say, so the conventional one would be to pick C, that it's trying to show you that the more sugar people eat, the more likely they are to get cavities. In this sample, 62% of respondents chose the right answer, which is, as sample surveys go, that's a pretty solid, not quite a supermajority, but it's, it's solid. But that does mean that sort of almost 40% of adults didn't pick the right answer or said that they didn't know. And so just in the same way that I don't advocate data visualization as some sort of magical tool for looking into your data and immediately seeing its true structure, when you're looking at it yourself as an expert, that's not true. It's also not true to say that just because something is presented in a graph makes it sort of immediately transparent and interpretable to your audience. And so you're always thinking about kind of both what it is that you can see when you're looking at your own data, and then how it is that the data that you're going to show people graphically will be interpreted by them. It's a relational process. So. So that's the motivation for looking at your data. Now, the other thing that we run into kind of almost immediately when we think about data visualization is that it's possible to do it badly and in ways that are confusing or potentially misleading. And again, it's kind of conventional in courses like this to start with a sort of parade of horribles, kind of a bunch of terrible examples. I won't do that too much, but it is true that some sorts of graphs are more difficult to interpret and understand than others, and more prone to being sort of just straightforwardly and erroneously interpreted by you or by the viewer. And it's worth asking kind of why that is. So for example, here is a default kind of chart you see in the business world all the time, even in some scholarly journals, the 3D bar chart. And if you ask people what values are shown on this graph, what is the value of A, B, C, and D? This is actually a surprisingly difficult question to answer if we look sort of carefully. Well, it seems like there's lots of information given to us. We've got the scale here and then it's even it helpfully draws these lines. But okay, what am I supposed to do? Am I supposed to go like this or like this, or sort of where is it, like 1.5? Is that what it's supposed to be? So it's sort of trickier than it looks. Now, often with these kind of graphs, the main thing the person wants to convey is, well, this is bigger than this, and we get that sense, right? That's okay. But insofar as anything sort of turned on actually knowing what the values were, it's a little trickier. You can try this yourself in Excel, which you probably have installed on your computer. It's just kind of 1, 2, 3, and 4. Although it really doesn't seem like that's the case, right? In a graph like this, and because of this, it's because of the sort of semi-isometric projection that the graph is drawn in that makes it sort of confusing, even with the grid lines going all the way across. Okay, so we've got three reasons graphs like this tend to be bad, and we'll talk briefly about each one of them. Graphs can go bad for reasons of bad taste, for reasons of bad data, and for reasons of sort of poor or bad perception, their perceptual qualities. And these are sort of increasingly interesting, I think, categories. So we've got bad taste, bad data, and bad perception. Now, we'll go through each of these in turn and just think about kind of how they might affect our way of thinking about things. The earliest and most common critique of a lot of graphs dating right back to the 1970s was, and with the advent of sort of software for drawing graphs in a quick and easy way, was that you ended up with a lot of junk in graphs. And the originator of this critique is Edward Tufte, whose book The Visual Display of Quantitative Information is justifiably kind of a classic in the field, and whose multiple sequels also explore what makes a good visualization. And so what Tufte argued primarily was that there was too much in too many of the graphs that he looked at, both in sort of scholarly books and articles, and especially out in magazines and on the news and so on. There was just sort of too much junk, chart junk, he called it, that was had nothing to do with the data being represented in the graph. And he suggested, or he argued, that what you should do is try to maximize the data to ink ratio, he called it, in your graph. That really as much of the ink on the page, as it were, or pixels on the screen, should be devoted to representing actual data in your graph rather than other things, extraneous features that aren't necessary to the presentation of the graph. And so, we can consider graphs like this. This one I drew in Apple's numbers spreadsheet. You got a very nice. You can do all kinds of things in these things if you push sort of hard enough. I'm not sure if it comes across on the screen. We've got a very, very pleasing sort of wood grain on these here. Looks nice. We got the shadows being cast, the lights coming from somewhere. Got the paper and the pinboard. We have papyrus, of course, papyrus font, everyone's favorite off-brand herbal tea font. And the point here is that there's 5 numbers being shown on this graph, and it's quite difficult to tell what they are. And so we really should be sort of simplifying this kind of thing. Tufte's own examples come from one regular target of his critique was the graphic designer Nigel Holmes, who's still around and doing very interesting. He does very cheerful infographics, but Tufte hated him. This kind of thing, right? That you have all of this extraneous kind of material, and we could represent this data sort of in a much more pedestrian way by just kind of having it in this regular old bar chart, or even more simply with a dot plot. We could reduce we could increase the data to ink ratio even further. And so one very common sort of, and again, reasonable approach is to sort of say, look, you really should be simplifying and minimizing all of that extra color or whatever it might be, all the various doodads in your graph. And so you get examples like this from Dark Horse Analytics, a company in this world, where you take stuff that's kind of, there's too much background color, too many lines, too much labeling, extraneous. For example, there's no reason to have this key here, right? Because they're already on the x-axis. That kind of thing. We'll think about more principled ways to think about this in the next session or two, and simplify it right down to focusing on the stuff that you actually care about. And as I say, this is a useful and important critique of a lot of bad visualization. It does have its limits, though, and so good taste kind of won't save us entirely, and particularly the relentlessly sort of thinking about maximizing the data to ink ratio. We can push that sort of a little too far. So here's an example again from Tufte. where we have three ways of drawing box plots. And so, um, as you probably know, box plot is a way of quickly summarizing a bunch of data, giving us a sense of the distribution. The thick line is the median. Usually, the bottom of the box is defined by the 25th percentile, the upper by uh, the 75th percentile in the data, and then we go out to usually the little dynamite handles here are the edges, the whiskers of the box plot are defined as by twice the interquartile range. That is twice the range of the up to twice the range of the gap between the 25th and 75th percentiles. And then sometimes we show like further outliers kind of higher up. As an aside, actually, the box plot was invented by John Tukey, one of the pioneers in exploratory data visualization and in hierarchical linear modeling, actually in the 1960s. And one of the things that he wrote this book, which I have it over here on my shelf. This book, this exploratory data analysis, which I think Wiley are going to reissue. It's a curious book because it comes from the age when computation is expensive and time consuming, and you have to put your data into the queue, to be sort of batch processed on the VAX in the middle of campus. And so what he's looking for always is sort of quick ways to numerically or visually summarize distributions fast. And so our kind of conventional 5-number summary, median, 25th, 75th, min, max, that's from this desire to kind of avoid having to actually send the data to a computer. And box plots come from that too, being able to quickly summarize distributions just using 5 numbers. And so now the computation is much cheaper. We can think about ways to sort of do the same thing, but that allow us to show the data in a more comprehensive manner. This is Tukey's original design for box plot. This is a slightly more refined design where the median line is thinned out. We have a solid line here. We remove these kind of dynamite cap things or plunger caps on each end, but keep the grid lines. This is Tufte's own sort of super minimalist box plot, where the median is defined by this dot. Now we have the lines. We shut down the we remove the border box and simplify the axis, and define the 25th. The box is gone in effect, but it's there kind of in terms of its negative space, and this is very elegant. However, it turns out that when you show these graphs to people who already know what a box plot is, they're quicker to read the values off and interpret this one, right, than they are this one. So even though the data to ink ratio is higher in this one, and it's more efficient in some sense, in that sense, at encoding the data that it's presenting, it's not as good, right? There's a certain amount of cognitive scaffolding and design scaffolding in here that helps people, and helps even people who already know what they're looking at, to just kind of process the information a little faster. So there are limits to kind of paring down your graph. Often we do need sort of a certain amount of framework to help us understand what it is that we're looking at. And so while kind of simplify is good strategy in many cases, and can avoid sort of some of the more papyrus-ridden three-dimensional kind of nightmares that we see in a lot of visualization, it's not sort of good taste itself is not sort of something that we can just kind of rely on to help us out of all the trouble that we might get into. And we can see this in cases where well-designed charts are misleading as well, or potentially misleading, which is our second case. So this is a graph from the New York Times a few years ago, redrawn from a paper by 2 political scientists, and this graph, the Times does very nice work graphically, and this is an example of a small multiple graph where we're effectively redrawing the same graph across a bunch of different countries over and over again. And it has a bunch of nice design features, some of them direct and some of them a little more subtle. So we can see that it has, amongst its virtues, right, it's very clear what the dots are here. You can see that we've got like a little error range that's been colored in, the confidence intervals. These are labeled for a general audience, just telling you what those are instead of, so that's good. You can see a number of other features too that are maybe less obvious. For example, we don't label every single tick on the axis. We don't have to do that. You see, and here it's even more subtle. We see 1930s to 1980s, and then it's just 30s to 80s after that. So you understand that it's by decade. Similarly, the lines here don't cross. We get a little bit of separation. And then finally, the ordering of the plot is also nice, right? Because it's not just in alphabetical order, which would be the default in many cases, but also the least informative. Instead, we've ordered it by sort of by the average, I think, over the course of the across countries, and so that gives us the eye has this kind of it has this visual rhythm that sort of tells us what's going on. Now, when you look at this graph, the title is "Percent of People Who Say It's Essential to Live in a Democracy." It does seem like what it's showing is people of different ages were asked, how essential is it for you to live in a democracy, or is it essential for you to live in a democracy or not? Yes or no? And that this is the sort of percentages of people who said that it was. But in fact, this data comes from the World Values Survey, and when political scientists who know that data saw it, they got a little annoyed because the original question is not, do you think it's essential to live in a democracy? It's on a scale of 1 to 10. How important is it to you that you live in a democracy? And when you ask people that, well, most of them give an 8, 9, or 10 answer. Now, it's not that there's nothing going on in this data, but what the original authors of the paper did was kind of take all the took the original scale, recoded it not as the number of people who said 9 or 10 as essential, and then and show the results, right? So here, this is not, by the way, kind of a problem of the y-axis not going to 0 or something like that, because it goes to 0 in both cases. It's just that the data have been kind of recoded in a way that's slightly misleading. Again, that's by not using the full scale, it certainly sort of makes the point in a compelling way, but one wonders whether this would have kind of made the New York Times if the original paper had this graph, rather than the other one. So the thing, I think the general lesson here to bear in mind is that, like, this kind of graph is really well executed from the point of view of, like, as it being a piece of design, and that doesn't matter if what's being shown is in some sense misleading, right? So these tools can't make you honest, right? They're not magic, and they can help you effectively convey a message. And in fact, in a way, there's a sense in which kind of really well-designed graphs are kind of more worrying, or I don't want to say worrying, but like a well-designed piece of visualization has a kind of visual rhetoric of its own, right? Because you recognize it as being something that looks like it was done by someone who knows what they're doing. And so you think, okay, that makes it more credible, and it does. However, it doesn't guarantee, that that's the case, or it doesn't guarantee that the person who's sort of showing it to you isn't trying to have their thumb on the scales in some way. And so because of that, we want to be concerned, like, that we want to not forget that using these tools effectively is not a means to kind of make you a more honest researcher, right? That's something that comes before the work that you're doing, and so you have to you use these tools, but again, they're in the same way that any tool that we use, fitting a model, reporting an interview, or drawing a graph. We can use those tools effectively, more or less effectively, to express these underlying points or the underlying truths of the data that we're investigating. But it doesn't make us say them if that's not what we want to do. And that's a sort of two-sided process in the sense that, on the one hand, it's easy to pitch. You might think, well, I'm an honest person. I'm not trying to mislead anybody, which I'm sure is true. But it's also the case, as I think, I don't know, Richard Feynman or somebody says, that, like, you are the easiest person to fool when it comes to looking at your data, because you want to find things in it. and that's why you're looking at it. and and so the category of the class of person who can be sort of misled by your elegant data visualizations includes you, and so you have to sort of bear that in mind. And that's especially true because of the perceptual features of graphs that make it more difficult that can lead us astray in various ways. And so anybody looking at your graphs, including you, is sort of sitting on top of you're a person sitting on top of this whole perceptual and cognitive machinery that allows you to see things in the first place. And these things can be done sort of more or less well. Now, good graphs take advantage of the way features of the way that our visual system works in order to um, effectively convey information. But our human visual system is not did not evolve to look at graphs, and uh, and as a result, when looking at graphs, things that it kind of did evolve to do can get in the way or make things more difficult. So now I'm going to show you some visual effects here, and they'll, depending on your viewing environment, which is itself kind of a relevant feature of things, how bright the room is, how bright your screen is that you're looking at this on, how large it is, and so on. These may be more or less effective as you go. Um, so this is the Hermann grid effect, which was discovered in the 1870s. Psychologists, as they started looking at human perception and what eventually becomes kind of the cognitive science of the visual system, started to notice sort of features of the human visual system that showed us that that looking at things is an active and complicated process, and it's just not the case that you have this kind of naive sort of picture of that your eyes are sort of like a window, and that the light passes through them and it projects onto like a movie screen or something in your brain, and there's like a little version of you looking at it, sitting in an armchair, looking at what's coming through. It's like, that's not how a visual system works. And so with this grid illusion here, what you'll see is illusory dots at the intersections of the but only the ones that you're not directly looking at. If you try to directly look at them, it will disappear. And that's because one of the reasons that happens is that your visual acuity is actually quite poor beyond a very narrow range that and your brain is doing a lot to fill in details around the edges. And so this can be seen it's possible to exploit features of kind of edge and contrast perception to induce, for example, the illusion that these lines are diverging when they're not. These are Fraser. This is a Fraser column illusion. These are called. There's a version of this by the same Scottish psychologist called. This is the Fraser diamond. You want to say I'll speak in this kind of illegitimately teleological or anthropomorphizing way. When I say your brain wants to say, well, it doesn't want anything in that sense. This is just the way it's working. But you want to say that this goes like this and this goes like this, right? And this goes like this. But in fact, it's just that's not what is happening, right? There's just a sort of repeating but alternating pattern here and here that's making you interpret this as sort of a divergent series when it's just a repeating one. And there's a bunch of these, and they can be quite, they can be sort of somewhat disturbing. Oh, this is I'm going to have to, I will switch. This is a PDF for various reasons. So what I'm going to do is I will switch over quickly to my, I should be able to show you an actual live version of this one. Let me just bring up the actual HTML. And here we go. All right, we'll switch over here to the Mac. Oh, we'll come up in the corner. So there's this is the same, and this is just on a browser rather than, here, I'll make it full screen. So here we have our two perfectly geometrical circles, but we can run this little GIF here. And there's no cheating kind of involved here as we go. There's it's just that contrast patterns induce um, illusions of shape change in ways that are kind of somewhat disturbing sometimes. Um, and so what you think you see isn't really what's there. The same goes, and here we're getting closer to things that are relevant for data visualization when we have contrast effects due to edges like this, right? So the human visual system is very good at detecting contrasts between things. It's less good, much less good, at figuring out the absolute brightness or luminance of things that it's looking at. And so one of the side effects of that is that if we take, for example, grayscale boxes like this here, and we move them so that they're next to each other, that they're together, then just in virtue of them touching, just in virtue of them sharing a border, contrasts appear to be higher, right, between one and the other. That it's easier to see the contrast between sort of say the bottom two rectangles that when they're touching each other than when they're not. This can also be seen sort of if we bring it out in the context of background contrast effects, right? So here all of these rectangles are the same luminance. It's the same shade of gray. But if we put a gradient behind them, then the rectangles on the right will appear to be lighter in color than those on the left. Let me go back here to the regular slides. Take it away. So one of the strongest examples of this is Edward Adelson's checkerboard illusion. And so here you see this this kind of computer-generated image of a checkerboard with a green cylinder sitting on top of it. And the point of this effect here is that the shade of gray in this square, the B square, is the same as the shade of gray in the A square here, which doesn't seem like a reasonable thing to say, but it is. And the original diagram or effect shows this, but I can show you a somewhat better version of it live. Let's go back to the mini here. So I should be able to. Oops. There we go. So there's like it's just running there as a loop. So we'll come back to the start as we just fill it in. The reason this happens, as I say, is because your eye is not a good light meter. It's very poor at detecting absolute differences in luminance. That's the reason why, and maybe some of you, if you've ever seen a professional photographer at work, or if you're a keen amateur photographer yourself taking portraits or something, then photographers carry light meters with them, right? This little thing that they hold up, and it tells them what the absolute brightness of the room is in lumens or some other kind of measure. And the reason they do that is because they know that their eyes adjust to whatever brightness is ambient in the room, and they're just very bad at telling actually how absolutely bright the room is or the setting is. And so your visual system, and again, I'm speaking in kind of illegitimately anthropomorphizing terms, but like it evolves to detect contrasts. One of the things it has to do is to say, okay, where are the solid objects in my environment, and how is light falling on them? And so it has to resolve questions like, is that thing over there, that might eat me, is that a bright object that's in shadow right now, or is it a lightly colored object that's or is it a dark object that's out in the open, in the direct sunshine? And so all of the cues in Adelson's illusion here are sort of tricking your visual system into thinking, well, look, there's this checkerboard pattern that repeats. Um, there's the cylinder that's casting a shadow. So that thing, this thing is surrounded by the B square is surrounded by darker squares. So therefore, it must be a light object with a shadow falling on it, a lightly colored object with a shadow falling on it. But it's not. Well, it is relatively, but it's the same shade as the one on the outside. So. Um, and the nice thing about sort of effects like this, and I use the word kind of effects uh, deliberately. You can call them kind of optical illusions if you like, but um, the visual scientists who do this, often they prefer kind of like visual effects as a term, because an illusion suggests that, you know, if you watch a conjurer or magician perform like a sleight of hand trick, and then they show you afterwards how it's done, then the next time you watch the trick, you can see, you can see where they palm the card, or you can see how they move. You understand, you can see through, as we say, right? You can see through the trick. But with this kind of thing, it doesn't matter how good a practical or theoretical understanding of the human visual system you have. You can't not have this happen, right? You can't consciously make yourself see the two things as the same shade of gray, because it's just happening at too low a level in your visual system to allow that to you can't override it consciously. You can just know that it happens, but so in that sense, it's not an illusion. It's just a feature of how you actually perceive the world, which is a little different. And these features are quite general. And so again, if you stare at this thing for a while, for 5 or 10 seconds or so, let's do that before while you're doing that, I will fix this over here. And if you do that, one of the things that might happen is that the colors just disappear as you look at them. No, they just go away, because your brain, it's like, well, nothing much seems to be happening here. Let's just say white, okay? As it sounds, there's a stronger version of this with a lilac chaser, which is again a version where in the slides you can look at it, and it will disappear as you go. All of these have to do with again the relationship between color perception, edge contrast perception, and our willingness to, or ability to kind of make inferences about that. So, for example, the intersection of color and contrast. Here, these two cloudy sort of images, one in grayscale and one in red and green, seem more or less equivalent in terms of their perceptual properties, unless you're colorblind, and in which case the one on the right might seem a little more homogeneous. But if we introduce edges into these pictures, this is the same picture, then you can see that we're much better at detecting edges in the black and white in the luminance channel than we are in detecting edges when it comes to reds and greens, right? So things still look blurrier. You can make out the edges in the right one, but it's still somewhat blurry. The same goes for this. This can come up in real cases quite often, right? So, for example, in these kinds of cases, this square is the same shade of brown as this one, and there are several others around this that graph that are also similarly the same shade, right? And it's because, and so if something depended in terms of our visualization on sort of checking the contrast here, we would be misled. Just because they both share a border and are surrounded by more lightly colored squares, we're just much less likely to think of this as the same shade of brown as this. So this can affect our interpretation of graphs as we make them, right? And so here are actually all of the squares on this graph that are the same color. It's easier to see when we highlight them, and mitigate a little bit the effects of looking at um, the borders, but it really does make a difference. And so the tools we use to represent when we encode data with color, for example, just like when we encode data with position or any other thing that we can look at, what we want is for the way that we've encoded it, we represent some number as a color, for example, we want that to be sort of a faithful representation of the value of that number in our data. And in particular, we want any differences in the value of the numbers in our data to be preserved somehow in the encoding by transforming them to a color or to a position on a line or something like that, so that there's a correspondence or an isomorphism between the structure of our data and the structure of what we're looking at visually. And it's very easy to break that depending on the kind of thing that we're looking at. So for example, with color is notorious for this, that sort of rainbow color schemes like this are very poor if we encode them as kind of linear features of our data. They're very poor at kind of representing equal space changes along the spectrum, because the perceptual difference between a step from here to here is not the same as the perceptual difference as an equally spaced step sort of further along the spectrum. And so rainbow spectra are quite difficult to interpret as a result. The tools that we do use, well-designed visualization tools, will take advantage of and will be deliberately constructed to try and make sure that they preserve that correspondence. Usually that means keeping things linear in the brightness channel as we move across a scale, because for many kinds of graphs, that's not the case, right? For many kinds of colors. And to finish this session, I'll show you an example from a weather map. So for instance, like what we want here with these kinds of graphs is for each of these scales, we want the sort of step, so to speak, from this to this to be perceptually the same as the step from this to this, right? And so we want it to be sort of a linear step as we go. And very often that's not the case. The same goes for color scales like this, where we have a point in the middle. That's a sort of midpoint that's diverging in this direction or this direction. We want the steps in brightness and color changes to be the same and to be equivalent. The same goes for cases where we have unordered categorical data that we want to label, and we don't want sort of one category to jump out at us just because it's bright red, unless we're doing that on purpose. Instead, we want the perceptual features to be kind of distinct and equal as we go. And so, for example, here is the Hurricane Dorian from a couple of years ago in the US. This is the one that then President Donald Trump drew on to indicate that it was heading towards Florida or Texas or somewhere. And so this is a standard map. This one is from the National Weather Service. And you can see that what they want to do, right, is have a scale indicating the probability of tropical storm force winds, and going from a probability of 0 to probability of 1 or 100%. Right? So this is like a linear scale, right? That's what they're trying to show us. And then they've divided it up into these segments where we go through different kind of color stages. And the difficulty with, and the perceptual difficulty with things like this is exactly sort of, well, we go from a darker here through these colors, we go to yellow, and then it's, it gets darker, and then it turns light again, lighter, and then green, right? It's not clear how we should be interpreting this. One way to think about it is that if empirically, like if I took this scale and I chopped up the pieces into individual bits, and then I asked you to order them from 0 to 100, what are the chances that you would reproduce this ordering, right? And it's not, maybe you would, but there's a bunch of different ways you could do it, right? And that's the problem, right? That because we want this to specifically be linear, but it's not. And we can see this if we replace this with a a color balanced scale that's almost the same, but is linear in the luminance channel, that when we go from left to right, it's steadily, it's keeping the sort of brightness right. Well, then we can see we can move from the dark to the light area while changing color, but in a way that's kind of more progressive, right? That goes from the white value indicating 0 probability all the way up to the 100% probability here. And this becomes this is easier to see in monochrome scales. Like if we take this scale and convert it to a monochrome scale, you can see the problem, right? So we're just taking away the color, and here you can see the problem is that this is what I mean when I say that the scale is not linear in its luminance, right? That its brightness changes across the scale in a way that's not helpful to us as a viewer. Whereas the second scale that we drew, this one, if we just convert that to a grayscale, we get the expected linearity in its luminance. So that's a sort of example where this is why we care about things like how our data is encoded and how it gets represented, because it's no matter how well designed your plot is in Tufte's terms, no matter how good your data is, if it's perceptually poor, then you'll mislead yourself or mislead other people as we go. And so what we're going to learn about as we go through is sort of principles for we're going to put to work these kinds of principles using tools that helpfully have most of them built in as a default, right? So we won't have to be sort of finding ourselves trying to choose unless we want to and make decisions about all of these difficult questions. But instead, we want a tool that kind of has sorted out a lot of these defaults for us in a way that's helpful.